how we start? So we start with the classification theorem. The classification theorem is this. So if pi is irreducible system, then its thinking diagram is one of the following, AL to GL. So we will this theorem. So yeah, we can just consider about the cosector graph, not thinking diagram. So it's cosector graph. Is one of the following. AL, BL, but CL is same with BL as cosector graph, and BL, E6, 7, 8, and F4, G2. So we don't need to consider about the length of root because in cosector graph there is no information about the length of root. Right? So we will work just with unit vector. And it's because working with unit vectors is easier than consider thinking diagram. So we need a definition. So that E is Euclidean space of dimension n. Dimension n. And that frac A is subset of E, E1 to epsilon 1 to epsilon n. This is called admissible. The subset is called admissible. If they hold 4 conditions. So the first condition is these vectors are linearly independent. The second condition is they are unique vectors. And third condition is epsilon I, epsilon j is less than or equal to 0 if I is not equal to 0. And fourth condition is for epsilon I, epsilon j squared is 0, 1, 2, or 3. It's if I is not equal to 0. So we recorded admissible subset. And they are the graph gamma of this admissible subset. Rectangle. So this is obviously have just n vertices, right? N vertices corresponds the elements of admissible subset. Fraction. And for EI, EJ axis, right? EJ, epsilon, scalar axis. So we record this graph of admissible, right? So this graph is same with just cosector graph, right? And this admissible subset always exists. This is because we have example. Its existence. they are a root system and they are a base, and there are a subset alpha 1 to alpha n. Then alpha 1 over square root inner product alpha 1 to alpha n over square root alpha n is admissible subset. This is because they satisfy these four conditions, because they are linearly independent, because this is elements of base, and they are unit vectors because they divided by their length, and they satisfy this condition because they are elements of base, right? So they satisfy this condition if you divide this length, right? And we need to check this only for first condition. So I will hold it by epsilon 1 to epsilon n. So check for epsilon I, epsilon j squared is same with, we can put this one here and this one here. So for alpha I, alpha j squared over alpha I, alpha j, alpha I, alpha I, alpha j, right? Because there is scalar. And then we know that this is just alpha I, alpha j, alpha I. Right? And we know this is 0, 1, 2, or 3. So this satisfies the first four conditions. So this is admissible. Okay, so we start proof, but it's divided in 10 steps, so it takes a lot of time maybe. So the first one is a subset of admissible. This is admissible, so this is subset of admissible. It's still admissible. This is very obvious because if you consider the graph, so it has the graph like cosector graph. For example, just for example. So you can choose subset like this, and it still have like cosector graph. So this is admissible, obviously. And the second claim is that the number of pairs of vertices in gamma connected by each other is strictly less than n. So yeah, they are pairs, right? Connected pair, something like this. This pair, the number of pairs, strictly less than n. So this is because set epsilon as summation of epsilon I. So epsilon I, this frag A has element epsilon 1 to epsilon n, right? So we can give sum. And then this is non-zero because the i's are linearly independent, right? Independent, non-zero. So because this inner product is positive definite, this is positive, right? And we can put this summation here and here, so we can get I to n, so we can get n plus summation 2 epsilon I, epsilon j, I is less than j. N is because just this one. So this is 1 because it is unique. So some is N. And if you change this one, they have same inner product. So there is 2. Yeah, and suppose there are connected vertices, so EI and epsilon I and epsilon j. This negative means they are connected, right? They're connected. Yeah, so that implies that for epsilon I, epsilon j square is no 0, 1, 2, or 3. Right, this is because by the definition of automorphism, so this implies that 2 epsilon I, epsilon j is less than or equal to negative 1, right? If you consider this condition. So we don't, because if you have more than greater than or equal to n pairs, they should be negative or 0. So this is contradiction. So this implies this condition. I would 0. Because if you put this negative 1, yeah. So yeah, the number of non-negative 1 should be less than or equal to n minus 1. That implies this statement, right? And claim 3 is that gamma contains no cycle. Consider there is a cycle, with k vertices. For example, like this. Then such pairs means pairs in claim 2. From 2. In gamma prime is greater than or equal to k, right? This is because if there, for example, if there are 3 vertices and there are more than 3 edges, so this is contradiction by 2. And then the fourth step is that the number of edges originated at one vertex of gamma is less than or equal to 3. So that means if there is a vertex epsilon and the total number of edges is less than or equal to 3. So this example cannot be answered, right? Because there are 4 edges from epsilon. So let epsilon and do 1 to do k be element of bracket A be distinct such that they're connected from epsilon. Like this. And the 3 claims tells us that there are no cycles, so epsilon I, epsilon j, always 0. This is because if they are connected, there are cycles, right? So this implies this condition. Instead, nu not prime as epsilon minus summation I is 1 to k epsilon nu I and do not as do not prime divided by do not prime. Then we can three results. The first one is that nu not prime and nu I is equal to, we can put this equation here. We get epsilon nu I, and the remaining term is just nu I nu j. So this is 0, right? Then just the one term is alike, nu I. So epsilon nu I. Right? But nu I is unit vector, right? So this is 1, so this is 0. So that implies that nu not and nu I also 0. It's because nu not is just do not prime by the length. And the second result is that we know that nu not is included in span epsilon nu I to nu k. This is because by definition of nu not prime, so this is in span here, and nu not also in the space of span. But this is non-zero because they are linearly independent and they have non-zero coefficient. And we know by the first result, do not and do I is always 0. So that implies that do not and epsilon is non-zero, right? Because do not is non-zero. Then the third result is that do not prime is, we can put this equation here. So epsilon do not prime, and the remaining term is 0. This is because by the first condition, right? First condition here, this is 0. So we have this relation, and then this implies that summation I is from 0 to k epsilon do I is same with we can epsilon do not plus summation from I from 1 to k epsilon do I. And that is equal to, if you put this equation here, you get epsilon do not prime over do not prime plus summation I k epsilon du I, right? But like this one, this is 1, right? Because they are same. And do not prime is just epsilon minus summation here. So it's the same with epsilon. So that implies that we know that epsilon is unit vector. So epsilon is 1, and this is same with by third result summation times 0 to k. Epsilon du I. No, we can put here, so we can get this k. Yeah. And then this implies that this is greater than summation k from I from 1 to k, not 0. Epsilon du I here. Then, and then this implies that 4 greater than 4 summation times 1 to k for epsilon du I here, right? And that is just the number of edges. So the number of edges is less than 4. That means proof is right. Then we can get the fifth plane, the only graph, gamma containing a trig edges. This G2 case, right? This is because of by 4. This is 4. The maximal number of edges is 3. So we cannot add more edges. And 6 is that let frame A prime as let epsilon 1 to epsilon k is a subset of admissible subset has subgraph like this simple graph is called simple. And this one is epsilon 1 to epsilon k. And then a prime we can define as a minus epsilon 1 to epsilon k union epsilon, where this is admissible, where epsilon is the summation of e which is from 1 to k. So to show admissibility, we need to check the 4 conditions. So the first one is linearly independent, but it's very obvious because there are no epsilon 1 to epsilon k, and this one is the summation of epsilon 1 to epsilon k. So this is linearly independent. Right. And the second condition was that they are unit vectors. So we know that elements of here are always unit vector because they're subset of A, but we need to check if epsilon is unit vector. So this is because, yeah, if you consider the graph, we know that 2 epsilon I plus 1 is negative 1 because there are one edge. And then the otherwise, this value is 0, right? So this implies that epsilon is summation. So you can have k plus summation 2 epsilon I epsilon j, but yeah, there are only epsilon I and epsilon I plus 1, right? Because the other term is 0. 1 to k minus 1. And then this is negative 1. So this is negative k plus 1. So this is 1. So this tells us epsilon is unique. And the third condition was epsilon I and epsilon j, inner product of epsilon I and epsilon j is less than or equal to 0. But we only need to check that if there is an element of here, nu and sigma satisfy this condition, right? So if nu is k minus epsilon 1 to epsilon k, and then yeah, it cannot be can be connected to at most one element, so epsilon 1 to epsilon k. This is because there are no cycles, right? There are no cycles. So if yes. Yeah, because epsilon I to epsilon k, they are connected, right? So if there are nu, so if there are two pointed connected with nu, so this is triangle, so this is cycle, right? So not yet. So at most one of right. So this implies that yeah, if there is no connection between nu to epsilon I to epsilon k, then nu epsilon is 0 because epsilon is summation of epsilon I. Or if there is one edge from nu to epsilon j, say j, then nu epsilon is same with nu epsilon j, right? Because the other term is 0. So we know that this is 0, 1, 2, or 3. So they, yes, that implies that nu epsilon is less than or equal to 0, right? And then the first condition also, oh no, sorry. Yeah, this is less than or equal to 0. Then the first condition was for epsilon, the nu epsilon square should be 0, 1, 2, or 3, but it is obvious this is because this is 0 or, yeah, we know that this implies that this is 0 or for epsilon j square, so we know that this is 0, 1, 2, or 3. So this A prime satisfies the four conditions, so this is admissible. Okay, so the claim 7 is that gamma contains no subgraph of the form. The first one is like this. The second one is like this. The third one is like this. This is because by using 6, we can denote it epsilon 1 to epsilon k, epsilon 1, epsilon k, epsilon 1 to epsilon k. And we can apply this 6's claim, so we can remove this point, these vertices, and we can add epsilon. So we can make like this, and we can make like this, and we can make like this. But they have 4 edges from these vertices. But this is contradiction by 4, right? This contradiction by 4. So is that any connected gamma of unadmissible set as one of the following forms. First one is this, like A, which is M. Then the second one is like this. The third one is that is obvious from 7. So we already know, triple edges. There are unique way to draw triple edges like this. We saw in 5, right? Yes. And then if there is 2 edges between 2 vertices, we cannot draw like this. So there are 4 vertices, 4 or 5 or 6 vertices like this. So they makes only these lines, right? So we know that this is only possible root system. Thinking that cosector graph, right? Then we know this is AL, this is G2 cases, so we just prove the only 2 cases is DL and F4, and the only 3 cases is DL and E6, 7, 8 case type. So the claim is that the only connected, the second type in 8 is only EL or F4 case. So I claim it. So So let's set. Oh, yeah. We want to know the name of vertices. So epsilon I, epsilon 2, and epsilon p. This is new 1, and new 2, and new q. And I give up later. So epsilon as summation I epsilon I for I for p. And then new as summation I do I from 1 to q. Now that if you consider the graph, we can know that 2 epsilon I, epsilon j, I plus 1 is negative 1, and 2 u j, and j plus 1 is negative 2. And the other case is orthogonal, so 0. That implies that epsilon epsilon is yes. Epsilon is summation I squared I 1 to p, right? This is because from I EI, so we can put I square and EI epsilon I is 1, right? This one plus summation 2 epsilon I plus 1 is from 1 to p minus 1, but we know that this is negative 1, right? So we can no. I plus 1, so I plus 1, epsilon I plus 1, but this is negative 1, so we can change this equation like this. Right. So this implies that by the calculation, this is a pp plus 1 over 2. It's easy to check. And similarly, nu is also q plus 1 over 2, right? By the same region. And then, we know that for epsilon p nu q squared, there is 2 edges between them. So this is 2. So this one is 1 over 2. So that implies that epsilon nu is there's only connection between them. And there's no connection between this epsilon and this nu. So this is just squared. P epsilon P Q epsilon Q, no, nu Q square, right? And this implies that P square, Q square, and there was 1 over 2. And then we use the Schwarz inequality. And we know that epsilon and nu are linearly independent. So linearly independent. Epsilon and nu. This tells us epsilon u scale is less than epsilon epsilon and nu nu. So yeah, I want to dissipation. Dissipation. So by A and B, we will use dissipation, so we can get p squared q squared over 2 is less than pq, p plus 1, q plus 1 over 4, right? And we can remove pq, and we can remove this one. So this implies that pq minus p minus q minus 1 is less than 0. And then this implies that p minus 1, q minus 1 is less than 2. And this implies that p and q are 2, or p is 1, or q is 1. And this gives us BL case, right? And this gives us F4 case. Right. Okay. So if p is 1 or q is 1, if p is 1 from this position, so this looks like this, right? And if p and q is 2, so we can remove this position, so we have F4 case. And then the last claim is that the third type, type in A is just BL or E6, E7, E8 cases. And I want to also denote a U11, U2, U1, P minus 1, and U2, 1, U22, and U2, Q minus 1, and U31, U32, and U3R minus 1, and I want to clarify this. Right. The proof is very similar with 9, so I want to define epsilon superscript I as summation I do superscript I. No. This is I, this is J, this is J. J is from, from 1 to P minus 1, or 1 to Q minus 1, or 1 to R minus 1. And then that implies that do superscript I is, do J. Yeah, there are no connection between them, so 0. And we know that epsilon superscript I is non-zero. There are connection, there are edges. And we apply the same method in the proof of 4, the first claim. So set do not prime as epsilon minus, but in the proof of 4, they was unique. But in this case, they are not unique, so quite different. Epsilon do superscript I, and do superscript I, do superscript I, and do I is from 1 to 3, and do not as same way, do not prime, square root, do not prime. So by the same reason, S4, we can get 3 results. So we will not check because this is obviously the same reason. So we have these 3 conditions, right? This one, and the last one is this summation is epsilon, right? Epsilon. Very easy. Same reason, we can get the result like nu naught and nu ji is 0, and epsilon nu naught is non-zero, and the last term is that epsilon plus is epsilon nu naught plus summation I from 1 to 3 epsilon nu I. So that gives us epsilon is just unit vector, right? Yeah, epsilon is just in the diagram, so unit vector. So epsilon is 1, and by the same reason, so this is greater than summation from I is 1 to 3 epsilon nu I square nu I almost done. And yeah, and do 1 is p minus 1 over 2. This is because we did showed that this one epsilon is p plus 1 over 2 in the claim 9 with the same reason, because this is from 1 to p minus 1, so p minus 1 over 2. So similarly, nu 2 is q minus 1 over 2. So we don't need to this. And that implies that this one, so epsilon nu 1 squared over nu 1 is that epsilon nu 1 is epsilon nu 1 is p minus 1. Yeah. You know, epsilon nu 1 is that epsilon p minus 1 nu p minus 1 squared. So you can get p minus 1 squared, but there is p minus 1. So there's p minus 1, and there is p, and yeah, and this one is just epsilon nu p minus 1 squared 4 is just 1 because there are 1 edges. So this is 1 over 4. So it's 1 over 4, and there is 2. So there is 2. So this implies that 1 over 2 or minus 1 over p. And similarly, we can apply also do 2 and do 3 case, right? So then we can get this summation 1 less than this summation epsilon ui squared ui is the sum of them. So 1 over 2 and 3 minus 1 over p, 1 over q, 1 over r. Right? And then this implies that 1 over p plus 1 over q plus 1 over r is larger than 1. And I want to multiply by c. And without loss of generality, we may assume that 1 over p is less than or equal to 1 over q, and less than or equal to 1 over r, and less than or equal to 2. This is because if r is 1, then just the graph is just AL case. AL case, so we don't need to consider this case, right? If r is 1, there are no vertices here, so it looks like AL. So we can assume this one. So so by C and D, 1 over r is less than or equal to 1 over 2, and 1 over r is the biggest one here, so this is greater than 1 over 3. That implies that r is just 2. And then if you put here 2, you can get 1 over p plus 1 over q is greater than 1 over 2, right? And B and E implies that yeah, 1 over q is less than or equal to 1 over 2, and this implies that this is greater than 1 over 4 because 1 over q is greater than 1 over p, right? So that implies q is 2 or 3. So q is 2 or 2 is 3. So if q is 2, so we can pick any p, right? So to satisfy this condition, right? But yeah, we just consider from 2, right? Any p, and if q is 3 and 2, so this is 5 over 6, so this need to greater than 1 over 6, so p need to less than 6, that means p is 5 or 3.
In the first case, you have having p is bigger than over 2 because this is smaller than 1 half, right?
Yeah, this case?
Yeah.
Yeah.
Okay.
And we don't need to consider about p is 1 because if p is 1, just AL. This is 4. So that implies this EL case, and that implies E6. This implies E7. This implies E7. E6. This is our proof of this theorem. Any questions so far? Then very quickly, section 12. This is not too long. Maybe 10 or 15 minutes. Yeah. Yeah, we need to construct this root system because we don't know if there exists, right? So we need to construct, but we we just focus on A and B case. So we're gonna just show A and B cases exist, and we can know about the kata matrix. AL cases like this, two and just one line, right? That one, this, and BL cases. BL cases two and negative one line. But in the last term, there are two lines. So the product of these two positions is -2, but the last one is shorter one. So this is bigger. Absolute value is bigger. So we can get this kata matrix. And CL case is very similar. Two. We can change the -2 to -1, right? And DL cases in the last count, the 3 point, they're quite different. So yeah, there's just one line, L minus 2 and L. So L minus 2 and L minus 2 and L. And between L and L minus 1, there's no line. So this is kata matrix. So construction. That E is just R to the N, and with just the user in product and the standard basis. And then define G linear combination of epsilon 1 to epsilon n. And this is called lattice, right? And construct AL case. In this case, I want to let E as L subspace of E R to the L plus 1 orthogonal to epsilon 1 plus epsilon L plus 1, and define I prime as I intersect with E. Then pi, we can find pi as the subset of I prime such that the length of alpha is 2. And we can easily check that, yeah, this is the length 2, so there are elements like this. This is the length 2. Consider this scarce, right? And we can easily check that this can be root system. If you check R1 to R4 cases, and then we can define base epsilon 1 minus epsilon 2, epsilon L minus epsilon L minus L plus 1, and we can easily check this is a base. And then if you make a kata matrix using this base, you can get this kata matrix correctly. Right. So yeah, there is A1 case. Yeah, A1 case exists, right? And I want to consider about bar group. What is the bar group of AL case? So the generator of bi group is like this, I minus ei plus 1, and this sends ei to epsilon I plus 1, epsilon I plus 1 to epsilon I, so this is correspond transposition in the symmetric group. So yeah, and transpositions generate 4 symmetric group, right? So we can easily get that the bar group is isomorphism to SL plus 1 symmetric. And let's look at BL case. Let's look at BL case. So E is just R to the L, and define pi as element of I. The length is 1 or 2. And we can easily check. This is root system. And we can define base. Yeah. So yeah, 1 or 2. So plus minus epsilon 1 is length 1 and plus minus. Oh, wrong. Yeah, this is negative. This is because the it's in not I prime. No. In E, so they need to orthogonal to this one. And plus minus G. And this is root system, and we can define a base like this. 2 to alpha L minus 1 minus alpha L, and so L. So this is base, we can check it. And then if you make kata matrix by using this delta, you can check this matrix. So the BL case exists. And what is the bar? So we looked about this one first already. Epsilon I minus epsilon I plus 1 is corresponds just transposition, right? And but we need to check about the last term, and this sends epsilon L to negative epsilon L. So bar group is permutation and chain design, right? So that implies that bar group is isomorphic to changing sign. So Z over 2Z to the L, because there are L elements in here, delta, and semi-direct product SL. And then CL case is very easy because it is just from DL case. So E is R L, and pi is defined by just the dual of root system of B. Yeah, I want to. So we can easily check. This is just plus minus 2 I. So this one is correspond this one, and this one is preserved. So plus minus epsilon I minus epsilon plus minus I J. Then delta epsilon I minus epsilon 1 minus epsilon 2 to epsilon, yes, and minus 1 minus epsilon L and 2 epsilon L. And we can check the kata matrix of delta is easy. And then bar group is the same because we already learned about the dual root system. A bar group of dual root system is isomorphic. So the same with BL case. And last. DL case, E is R to the L, pi is just I, our length is 2, and we can check if this is just plus minus epsilon I plus minus epsilon j. And delta can be defined as epsilon 1 minus epsilon 2 to epsilon L minus 1 minus epsilon L and epsilon L minus 1 plus epsilon L. And we already know this is correspond transposition, right? I plus 1. Right? If I read this one, I see. Yes, this one transposition. Okay, we just need to check this one. So epsilon minus 1 plus epsilon L sends epsilon L minus 1 to negative epsilon L, and epsilon L is to negative epsilon L minus 1. So there are two negative signs. So they can only even numbers of negative sign. So if there are odd numbers of negative sign here, 1 to m n minus 1. The last one is definitely should be negative sign, right? So this is just determined by this L minus 1 elements, right? So this tells us this phi group is Z to Z over L minus 1, then the product S N as L. Right. We don't have much time, but I just want to explain the last subsection. But it is very easy to check. So the first thing is that automorphism is isomorphic to semi-product gamma.
Go, but please continue and finish. Okay, thank you very much.
Yeah, subdirect product gamma and phi will gamma is elements of automorphism satisfying how but it's very easy to check because this is normal subgroup from example in section 9, and easily check. And the thing 2 is that gamma may be identified as the automorphism of is thinking diagram. This is just because there is gamma, and gamma preserved base, so the vertex is preserved, right? And because gamma is included in automorphism, so alpha beta is the same with tau alpha, tau beta. Because they have same edges, that means automorphism, right? And then if there is an automorphism from position 11.1, we know that there exists uniquely exists the gamma prime in automorphism prime. But we know that this automorphism means they preserve the basis, so base. So that tells us gamma prime, tau prime is in gamma. That's it. This is for in section 12. Any questions so far?